What if you could find a shortcut? A way to really get your head around something complex, turning, a huge pile of technical stuff into insights you can actually use.
Well, that's pretty much what we're trying to do today.
Right? This is the deep
We're
dive.
digging into the core ideas of software craftsmanship, specifically from Robert C. Martin's Clean Code series.
But it's not just for coders, is it?
Not at all. It's really about the discipline, maybe the artistry of creating anything well. Software, sure, but also reports, plans, you name it.
Exactly. So our mission is to pull out those key nuggets, the stuff that really works in practice, so you get informed without drowning in detail.
And we're starting with something anyone who's built anything complex will recognize: the total cost of owning a mess.
Oh, yeah. That sounds familiar.
If you've ever, worked on a project that gets complicated, software, a creative thing, even just organizing something, you feel that drag, right? The mess. Martin points out, for programmers, messy code just slams the brakes on productivity. Teams start fast then, grind to a halt.
Every little change feels huge.
Yeah, like you touch one thing and two other things break. It's this tangled mess.
And your speed just tanks. It gets
Yeah.
closer and closer to zero, right?
It actually asymptotically approaches zero. And what's really interesting is how management often reacts.
Let me guess. Throw more people at it.
Exactly. They add more staff, hoping to boost output.
Mm-hmm.
But, and this is the crucial bit, it often backfires.
How so?
Well, the new people don't know the existing mess, they're under pressure to deliver, and they tend to make more messes.
Oh, wow. So adding resources actually makes it worse.
It can, yeah. It drives productivity down even further. It's
Yeah.
this really insidious cycle.
A vicious cycle. And that eventually leads to the big one.
The grand redesign in the sky.
Yep. Everyone throws up their hands, says we need to start over. A special team gets formed.
The Tiger Team, yeah. To
Yeah.
build a shiny new thing. But here's the catch. They also have to keep the old messy system running and updated.
That sounds like a nightmare scenario.
It often is. The book mentions seeing this drag on for 10 years.
So in years.
And sometimes the brand new system ends up being just another mess by the time it's done.
Oh, no.
Which brings us to this key idea Martin calls LeBlanc's law.
What's that?
Later equals never.
Later equals never. That's stark.
It really is. It's a warning against putting off the cleanup. The idea that you'll fix it later, well, that later just doesn't arrive on its own.
You have to actively make it happen.
Exactly. Or the mess just becomes permanent, crippling. It really forces you to think about the true cost of delaying that essential work.
Okay, so we've established the pain, the ever-increasing cost of a mess. But what's the flip side? How do we actually build something clean?
Right. Let's unpack what clean code really means, because it's more than just rules. It's presented as, like, a whole school of thought.
Like martial arts.
Kind of, yeah. Martin frames it like that. Different masters, different schools. His approach, his absolutes, are within his school. Doesn't mean other schools are wrong, but the value comes from really committing to a disciplined approach.
Interesting. So what do these different masters say clean code looks like?
Well, you have Grady Booch, for instance. He says it's simple and direct. Code that reads like well-written prose.
I like that. Code as a story.
Yeah. And Ward Cunningham, another big name, he says clean code shouldn't surprise you. It should just feel
Yeah.
obvious,
Mhm.
compelling.
Makes sense.
He also has that great line, beautiful code makes the language look like it was made for the problem.
Ah, so it's about making the language fit the problem, not just using language features.
Precisely. The craftsperson bends the language, makes it elegant for the specific task.
And this focus on clarity, it sounds like the code itself becomes the main design document.
That's a key takeaway. The code is the design. Forget fancy diagrams sometimes. The code is the truth.
Okay, and this ties into communication, right?
Massively. Get this. The ratio of time spent reading code versus writing it.
I remember this part is huge.
It's well over 10.1. 10 times more reading than writing.
Wow, over 10 to 1. So,
Yeah.
wait, that means making code easy to read is way more important than making it quick to write.
That's the implication. If you want to go fast, ultimately, you have to make your code readable, because you're constantly reading the surrounding code to figure out what to do next.
You can't build on a foundation you can't understand.
Exactly. And this isn't a one-time thing, it's continuous, which leads to the Boy Scout rule.
Right. From the Boy Scouts, what is it again?
Leave the campground cleaner than you found it.
Simple, but powerful.
Very. It's not about huge, risky cleanups. It's about small things. Every time you touch some code, maybe rename a variable, split a function that's a bit too long, remove a tiny bit of duplication.
Just constant small improvements.
Yeah, those little acts of care, they prevent the rot that slow decay into a mess. If everyone does it, the quality just keeps improving.
Okay, so philosophy, ongoing commitment, check. But let's get practical, down to the nuts and bolts. Naming things. This seems surprisingly important in the book.
Oh, it's fundamental to core idea. Names must be intention revealing,
Meaning.
meaning the name of a variable, a function, a class, it should tell you why it exists, what it does, and how it's used.
And if you need a comment to explain the name,
Then the name has failed. Like the example, infd, elapsed time in days.
right, deity tells you nothing.
Compare that to incalax time in days.
Yeah.
Instantly clear, no comment needed.
You get it immediately.
And the flip side is avoiding disinformation. Don't use names that mislead.
Like HP for hypotenuse. Could be Hewlett-Packard.
Exactly. Or worse, using a lowercase l or an uppercase O as variable names.
Oh, because they look like 1 and 0.
Mm,
Nightmare.
total nightmare. Wastes so much mental energy just deciphering.
The real takeaway here feels like programming isn't just talking to computers, it's mostly talking to other humans.
That's it. Or your future self. Clarity isn't a luxury. It's essential for collaboration, for maintenance, for actually making progress.
Makes sense. And this applies to making names pronounceable and searchable too.
Yep, forget old stuff like Hungarian notation like B for Boolean or member prefixes like M. Modern tools make those obsolete. Use names you can actually say out loud, names you can easily search for.
And context. Sometimes names need context, right?
They do. But add meaningful context, not gratuitous context. The book has that good example. Instead of just number, verb, plural modifier floating around.
You create a class.
Yeah, like guest statistics message. Suddenly, those variables make sense because they're inside that named context. It's instantly clear what they relate to.
Okay, names are crucial. What about functions? The book calls them the verbs, right?
And the first rule for functions is they should be short. Really short.
How short are we talking?
The guideline is hardly ever be 20 lines long. Ideally, much shorter. Like Kent Beck's example where functions were just 2, 3, or 4 lines long.
Wow. That's tiny. Each one just doing one tiny thing.
Exactly. Which leads to the core rule. Do one thing.
But one thing can be tricky to define.
It can. The book clarifies it. A function does one thing if all its steps are at the next level of abstraction down. It's about staying consistent within that level.
Okay. Like that render page with setup stand 2 downs example.
Right. Sounds like 3 things, but the TO-paragraph description shows it's one conceptual task at its level. To render page with setups and peer downs, we check if it's a test page, include setup steer downs if needed, then render the HTML. That frames it as one job.
Got it. And function arguments. Less is more.
Definitely. The ideal number of arguments is 0. Monadic, 1 argument is next best.
Why? What's wrong with arguments?
They add conceptual complexity. They make testing harder. And output arguments where you pass something in to be modified, they're really problematic. Hidden side effect.
And flag arguments, the Boolean ones.
Oh, those are called a truly terrible practice.
Why so strong?
Because a Boolean flag immediately tells you the function does at least 2 different things, one for true, one for false. You should just split it into 2 separate, clearly named functions.
Makes sense. Avoid the if, flag else, do that inside one function.
Exactly. And dyads, 2 arguments, are okay sometimes, but triads, 3 arguments, are often confusing.
Like assert equals, message, expected, actual. I always mix those up.
Everyone does. It's easy to swap expected and actual. The better way is often to group related arguments into a dedicated object. Pass one object instead of 3 separate things.
Ah, okay. Fewer things to juggle mentally.
Right. Another big one. No side effects.
Meaning the function only does what its name says.
Precisely. A side effect is when a function changes something outside its own scope unexpectedly. The book calls them lies, because the function promises one thing but secretly does another. Devious.
Okay, so pure functions are the ideal. How about errors? Error codes or exceptions?
The book strongly prefers exceptions over returning error codes. Why? Because it separates the error handling logic from the main happy path logic. Your primary code stays cleaner, easier to read, without being cluttered by if error code checks everywhere. It becomes a try-catch structure.
But there was a catch, right? With checked exceptions.
Ah, yes. Checked exceptions, the ones Java forces you to declare or catch, can violate the open-closed principle.
How?
Well, imagine a low-level function adds a new checked exception. Now, every single function that calls it, all the way up the call stack, has to be modified to declare that new exception too, even if they don't care about it.
Ouch. That forces changes everywhere. Breaks the closed for modification rule.
Exactly, it cascades.
Yeah,
So while exceptions are generally good, checked exceptions can be problematic for maintainability.
good point. And when you do throw an exception,
Provide context. The exception message should tell you what failed and where, enough to diagnose the problem.
okay, and this is a big one I remember. Don't return null.
Yes. Huge emphasis on this. Returning null basically invites errors.
The infamous null pointer exception?
Right. It forces the caller to constantly check if result, that's null. The book says code gets littered with these checks.
So what's the alternative to returning null?
Either throw an exception if it's truly an error state, or return a special case object, like an empty list instead of null, or a specific object representing not found.
Ah, so the caller doesn't have to do the null check. They can just treat the result normally.
Exactly. It makes the calling code much simpler and safer.
Okay, names, functions, errors. What about comments? The book seems almost anti-comment.
Huh. Well, the quote is, "Don't comment bad code, rewrite it."
That's pretty direct.
It is. The philosophy is that comments are, at best, a necessary evil. Clear, expressive code is always the primary goal.
So if you feel the need to write a comment,
First, ask yourself, can I change the code itself to make this clear? Rename a variable, extract a function, explain yourself in code. That's the mantra.
challenging, but I see the value. It forces better code.
Definitely. But that doesn't mean all comments are bad. There are good ones.
Like what?
Legal stuff, like copyright notices. Sometimes informative comments, providing essential context you can't easily put in code, maybe explaining a complex regular expression. Explanations of intent, why you did something a certain way, clarifications of obscure things, warnings.
Toadios.
Todos are okay, yeah. And documentation comments like Java docs for public APIs are essential.
But the bad comments, that list seemed longer.
It often is. Mumbling comments that don't really explain anything. Redundant comments that just state what the code obviously does. Misleading comments that are out of date. Those are dangerous.
And dated comments that are just noise.
Yeah, like requiring a comment for every function, even if it's obvious. And journal comments, tracking, changes. That's what source control is for.
So the takeaway is strive for code clarity first. Comments are the fallback, the necessary evil sometimes.
That's the essence of it. Make the code tell the story.
Okay, let's zoom out a bit. Structure and organization. How the code looks matters too, right? Formatting.
Absolutely. The book uses that great newspaper metaphor.
Yeah. Tell me about that again.
A source file should read like a newspaper article. High-level summary at the top, details increasing as you go down. The file name is the headline. The top functions give the big picture.
And visually like a newspaper.
Yeah, use vertical openness blank lines to separate concepts, like paragraphs. But keep tightly related lines of code, vertically dense, close together.
Makes it scannable. What about vertical distance?
Keep related things close. Declare local variables right where you use them, usually at the top of their function. But instance variables, the class-level ones,
Where should they go?
declare those all together at the top of the class. It's one well-known place to see the state of the object.
Okay. Horizontal formatting. Keep lines short.
Yep, the suggestion is around 120 characters max. Avoid that annoying horizontal scroll. And resist the temptation to horizontally align everything, like variable names or equal signs.
Why not? It can look neat.
It can, but it often emphasizes the wrong things and can actually make the code harder to parse because your eye gets drawn down their aligned column instead of across the lines logic.
Interesting point. An indentation.
Critical.
Right.
Non-negotiable. It shows the structure, the hierarchy. Code without it is basically unreadable.
And for teams.
Agree on one style and stick to it. Consistency trumps personal preference every time when it comes to team readability. Use automated formatters.
Good advice. Okay, next big topic. Objects and data structures. There was this idea of anti-symmetry.
Right. This is a really core distinction. Objects hide their data behind abstractions, and they expose functions that operate on that
They'll
data.
tell you what they do.
Exactly. Data structures, on the other hand, they expose their data. They generally have few, if any, significant functions or behaviors attached. They just hold data.
They're fundamentally different. Opposites, almost.
Pretty much, and this leads to a trade-off in how you structure your code.
How so?
Procedural code using data structures makes it easy to add new functions that operate on existing structures. But adding new data structures means changing all the functions. Object-oriented code is the reverse. It makes it easy to add new classes, new types, without changing existing functions, thanks to polymorphism. But adding a new function, a new method, might require changing many classes.
Ah, so it depends on what kind of change you expect more often.
Exactly. Knowing this helps you choose the right approach.
And this relates to the law of Demeter, or train wrecks.
It does. The law of Demeter basically says a method should only talk to its immediate friends, its own members, parameters, objects it creates, or global variables, not friends of friends.
So no long chains, like get this dot get that, get the other thing.
Right. Those are the train wrecks. It means your code knows too much about the internal structure of other objects. It's brittle. You should tell objects what to do, not ask them for their insides so you can operate on them.
Hide the structure. Makes sense. What about DTOs? Data transfer objects.
Yeah, those are basically simple data structures, often just public variables, used to shuttle data around, especially between layers, like from a database or over a network. No real behavior.
And active records.
Those are like DTOs, but with some basic database methods added, like save or find. The book warns against putting real business logic in them, though. Keep them focused on data representation and persistence.
Okay, got it. Now, classes themselves. Rule number 1.
Classes should be small.
And rule number 2.
They should be smaller than that.
Huh. So even smaller than you think. Like functions.
Exactly. Small is good. And the name is often the first clue. If you can't find a concise name, maybe it's doing too much, watch out for names like processor, manager, super. They often signal too many responsibilities.
Which brings us to the SRP.
The single responsibility principle. Probably the most important principle for class design.
And that is?
A class or module should have one and only one reason to change.
One reason to change. How do you identify that?
Think about the different actors or forces that might cause this class to need modification. If there's more than one distinct reason, like it handles business logic and database persistence and formatting for the UI, then it has too many responsibilities. Split it up.
So it's about isolating change.
Precisely. It helps you manage complexity. A developer changing persistence logic shouldn't have to worry about or accidentally break the UI formatting logic in the same class.
And making classes smaller and focused leads to more classes.
Often, yes. Many small, highly cohesive classes. Cohesion means the parts of the class belong together. They work on the same core responsibility.
The book had that print primes example, right? Refactoring a messy function.
Yeah, a fantastic example. Knuth's original program was one big function. The refactored version ended up being a system of small, well-named classes and functions.
And they didn't just rewrite it.
No. Crucially, they started with tests for the existing code. Then they made tiny, incremental changes, always keeping the test passing. Breaking up the big function naturally revealed opportunities to extract these small, cohesive classes. An emergent design.
Very cool. Okay, moving up to the system level. Systems and boundaries. It's all about managing change, isn't it?
Fundamentally, yes. Good software design anticipates and accommodates change without needing massive rework every time. It's about reducing the risk of change.
And the OCP helps here. Open-closed principle.
Definitely. Classes should be open for extension but closed for modification. You should be able to add new behavior without touching existing working code. Usually through inheritance or interfaces, drop in a new module.
And the DIP, dependency inversion principle.
That's about isolating components from each other. Depend upon abstractions, not on concrete details. High-level policy shouldn't depend on low-level implementation. Both should depend on interfaces or abstract classes.
So things aren't tightly coupled.
Exactly. It gives you flexibility. You can swap out implementations like changing your database without rewriting your core business logic, as long as both depend on the same abstract interface.
And separating construction from use helps with this, like the separation of main idea.
Yes. Keep the messy business of creating objects separate from the logic of using them. Move construction to a main function, or use factories.
What do factories do?
They encapsulate the creation logic. The application decides when to create something, but the factory knows how. It keeps the creation details hidden.
And dependency injection fits in here too, DI.
DI is a powerful way to apply this. Instead of an object creating its own dependencies, like a database connection or a logger, those dependencies are injected from the outside. The object just declares what it needs.
So it focuses just on its job.
Right. It promotes loose coupling and testability. Very important for larger systems.
All this seems to support the idea that you don't design everything perfectly up front.
Absolutely. The book tackles the myth of getting systems right the first time. It's usually impossible.
So what should you do?
Postpone decisions until the last possible moment.
Sounds like procrastination.
It's not lazy, it's strategic. Make decisions when you have the most information. Build the simplest thing that works, get feedback, learn, and then evolve the architecture. Delay commitment.
Adapt as you go. Makes sense. And finally, DSLs, domain-specific languages.
Yeah, this is about creating mini languages or fluent APIs tailored to a specific problem domain.
So the code reads like plain English for that domain.
Ideally, yes. It closes the gap between the business concept and the code implementing it, makes it easier for domain experts and programmers to understand each other, and reduces the chance of misinterpretation.
Very powerful. Okay, shifting gears slightly, but hugely important. Testing.
Crucial. And the book's stance is strong. Tests are not second-class citizens.
They're just as important as the main code.
Absolutely. They need the same level of care, design, and cleanliness. Dirty, hard-to-understand tests are almost worse than no tests.
Why worse?
Because they give you a false sense of security and they become anchors, preventing you from refactoring the production code because updating the tests is too painful.
And the main benefit of good tests.
They enable flexibility. They are the safety net. With a good test suite, you can refactor and change code fearlessly. Without tests, every change is risky, so you avoid improving the code. Tests keep code maintainable.
Which ties into TDD, test-driven development.
Directly. The 3 laws of TDD force you into this tight cycle.
Okay, what are they?
1, don't write production code unless you have a failing unit test. 2, don't write more of a test than is needed to fail or not compile. 3, don't write more production code than needed to make the current failing test pass.
Write test, make it fail. Write code, make it pass. Repeat.
Exactly. A very short cycle, maybe 30 seconds, leads to dozens of tests per day and ensures all production code is tested.
And this leads to cleaner tests, too, a domain-specific testing language.
Yeah, as you write tests, you refactor them, extracting common setup or assertion logic into helper methods. This creates a specialized API just for your tests, making them more readable, almost like specifications.
Interesting. And there's a dual standard for test code.
Right. Tests must be clean, readable, expressive. But they don't necessarily need to be as efficient, CPU or memory, as production code. Cleanliness is paramount. Performance is usually secondary for tests.
Good distinction. And practical tips for writing tests.
Minimize the number of asserts per test. Ideally, just one logical assert. And each test function should focus on a single concept. Test one thing at a time. Makes failures easy to diagnose.
And the FIRST principles?
Yes, the acronym for clean tests.
Right.
It should be fast, run quickly, independent, don't depend on each other, repeatable, same result every time, anywhere, self-validating, clear pass-fail result, and timely, written just before the code they test.
FIRST. Got it. Now, the really hard stuff. Concurrency.
Yeah, the book calls writing clean concurrent code hard, very hard.
Why so difficult?
The main issue is that concurrency bugs, race conditions, deadlocks, are often not repeatable. They show up randomly under specific timing conditions.
So they get dismissed as glitches.
Exactly. One-offs. But they're real bugs waiting to cause chaos.
The book had that simple increment example, right? Plus last ID used.
Yeah. 2 threads doing that at the same time. You expect, say, 43, then 44. But because the read, increment, and write steps aren't atomic, both threads could read 42, both increment to 43, and both write 43 back. One number gets lost. Subtle, nasty bugs.
Yikes. So how do you manage this?
Key principle: separation of concerns. Keep your concurrency logic separate from the rest of your code. Use standard concurrency patterns. And critically, limit the scope of shared data. Keep the sections of code where multiple threads access the same data as small and controlled as possible.
Protect the critical sections.
Right. And know your basic concurrent algorithms. Things like producer-consumer, readers-writers, dining philosophers. Understanding their patterns and pitfalls helps a lot.
What are common pitfalls?
Dependencies between synchronized methods are dangerous. If one synchronized method calls another on the same object, you can get deadlocks. And always keep synchronized sections small. Locking is expensive. It causes delays and contention. Minimize the time you hold a lock.
The anecdote about client-based locking was wild.
Oh yeah, the mainframe system locking up randomly because one programmer forgot to acquire the lock around a shared buffer. It's a perfect example of why relying on clients to manage locking is fragile. Better to encapsulate locking within the shared resource itself.
Makes sense. How on earth do you test this stuff then? If bugs are random?
It's tough. Strategies include Running tests many, many times, sometimes varying parameters randomly, Monte Carlo testing. Running tests constantly on all different hardware and OS configurations, and actively instrumenting code to increase the chances of bugs appearing, adding sleeps or yields at key points, called jiggling.
Trying to force the bugs out into the open? Wow.
It's a whole different level of difficulty.
So after all this,
Hmm.
names, functions, classes, tests, even concurrency, what's the overarching lesson? The book had that args class refactoring example.
Yeah, that example beautifully illustrated the meta lesson. First, make it work, then make it clean.
You don't write perfect code the first time.
Almost never. To write clean code, you must first write dirty code and then clean it. Get something functional, even if it's messy. Then, protected by your tests, you refactor. You make those small incremental improvements, cleaning it up step by step, always keeping it working.
It's a process, continuous refinement.
Exactly. It's craftsmanship. It's those million selfless acts of care.
Okay, wow, that was quite the journey. A really insightful deep dive. We've gone from the cost of a mess through naming, functions, errors, structure, testing, all the way to concurrency.
Yeah, we covered a lot of ground from Martin's clean code. And the core message seems to be that these aren't just, technical rules for programmers. They're really fundamental principles for building anything well, anything that needs to be robust, understandable, and adaptable.
Right. It applies way beyond just software. It's about clear communication, precision, managing complexity.
By taking these ideas seriously, you can avoid that pain of the ever-growing mess, that dreaded grand redesign. You can actually make progress faster in the long run and just work more professionally, more effectively.
Moving from just making it work to actually crafting something.
Mm.
Well, clean, understandable, maintainable.
And, the source material has that line. Quality is the result of a million selfless acts of care, not just of any great method that descends from the heavens.
Oh, I like that. It's the small things adding up.
It even mentions studies showing that something as simple as consistent indentation style correlates with lower bug density. Statistically significant.
Wow, really? Just indentation.
Apparently so. Which leads to a final thought for you, the listener. If even indentation can matter that much, what seemingly small acts of care in your own work, or whatever field you're in, might you be overlooking? What small, consistent efforts could fundamentally transform your results?